Have you ever wondered about the stars that twinkle in the night sky? What if I told you some of them are not what they seem? Among the celestial bodies that decorate our universe, white dwarfs are truly fascinating. They are the remnants of stars, much like our own sun, that have exhausted their nuclear fuel and are in their final evolutionary state. Now you might be thinking, what's so special about a star that's run out of fuel? Well, despite their seemingly uneventful state, white dwarfs are anything but dull. They are incredibly dense and hot when they are born, packing a mass comparable to our sun in a space no larger than Earth. Imagine trying to squeeze an elephant into a shoebox, and you'll get a rough idea of how dense these white dwarfs are. But it doesn't stop there. Just like a freshly brewed cup of tea that's left to cool, these white dwarfs begin to cool down and fade over billions of years. But don't be fooled by their cooling state. As they cool, they continue to glow with a faint white light, hence their name, white dwarfs. You see, white dwarfs are a testament to the universe's ability to recycle and repurpose. They represent the final stage in a star's life cycle, but their existence doesn't end there. Over time, they might accumulate enough matter to reignite nuclear fusion or even explode as a Type II supernova, making room for new stars to be born from their remnants. So the next time you find yourself gazing at the night sky, consider the incredible journey of these stars. Remember that some of those twinkling lights might not be stars in their prime, but white dwarfs, slowly cooling down, like a cup of tea left on the counter. Their subtle glow is a silent reminder of the universe's endless cycle of birth, death, and rebirth. So, next time you look up at the night sky, remember, some of those twinkling stars might be white dwarfs. So, what happens in the life of a white dwarf? They don't just pop into existence, do they? Well, they certainly don't. The birth of a white dwarf is a tale of cosmic evolution, a testament to the life cycle of a star. Imagine you're a star, not the Hollywood type, mind you, but a glowing, burning sphere of plasma in the universe. Your life begins in a nebula, a vast cloud of gas and dust. Over time, gravity pulls this material together, and you're born as a main sequence star, much like our own sun. For billions of years, you shine brightly, radiating energy into the cosmos. You're in your prime, fueled by nuclear fusion, turning hydrogen into helium at your core. But alas, nothing lasts forever, not even in the vastness of space. Over time, you burn through your hydrogen fuel. It's a bit like a car running on fumes, sputtering towards the inevitable. When you've exhausted your hydrogen, you begin burning helium, causing you to expand into a red giant. Your outer layers puff up and you become hundreds of times larger. Yet this phase too comes to an end. Eventually, you've burned through all your fuel. You've given it your all. And now it's time to shed those outer layers. This process creates a beautiful planetary nebula, leaving behind a hot core. And voila! You've become a white dwarf, the stellar equivalent of a car running on empty. You're no longer undergoing nuclear fusion, but you still glow with the residual heat from your previous stages. You've entered a long cooling phase, where you'll slowly fade over billions of years. So, in a nutshell, that's the life of a white dwarf. It's a journey of transformation, from a vibrant, fusion-powered star to a slowly cooling ember. It's a tale of cosmic resilience, of how even in the face of exhaustion, a star continues to shine, albeit in a different form. So, much like a car running out of gas, when a star runs out of its fuel, it becomes a white dwarf. Now, let's delve into the physics of white dwarfs. Don't worry, I promise not to get too technical. Imagine a room full of bouncy balls, each one zipping around, bouncing off the walls and each other. Now imagine if you tried to squeeze that room smaller. What would happen? That's right, the bouncy balls would push back against you, resisting the squeeze. This is a bit like what happens inside a white dwarf, a type of star that has exhausted its nuclear fuel and collapsed into a dense, hot core. You see, the core of a white dwarf is jam-packed with electrons. These little subatomic particles are a bit like our bouncy balls. They're zipping around at crazy speeds, bouncing off each other in the star's dense core. This creates a pressure, known as electron degeneracy pressure. Now, normally the immense gravity of a star would cause it to collapse in on itself. But in a white dwarf, this electron degeneracy pressure pushes back against the star's own gravity, preventing it from collapsing. Just think of those bouncy balls again. If you tried to squeeze the room smaller, the bouncy balls would push back, right? The same thing happens inside a white dwarf. The electrons push back against the star's gravity, keeping it from collapsing. But here's the really fascinating part. This balance between electron degeneracy pressure and gravity is incredibly delicate. If a white dwarf gains too much mass, it can tip the balance and cause the star to explode in a spectacular fashion, an event known as a supernova. But that's a story for another time. For now, just remember this. Inside every white dwarf, there's a room full of bouncy balls, or rather, electrons, resisting the squeeze of gravity. So, just like bouncy balls in a room, the electrons in a white dwarf push against each other, keeping the star from collapsing. You might be wondering, why are white dwarfs important for us to study? Well, these tiny celestial powerhouses have a lot to teach us about our universe and our place within it. White dwarfs are the remnants of stars that have exhausted their nuclear fuel. Over billions of years, they cool and fade away, but they don't go quietly. As they age, white dwarfs hold the keys to unlocking some of the biggest mysteries of the universe. One of the most profound things we can learn from white dwarfs is the age of our galaxy. You see, the cooling of a white dwarf is a process that occurs at a predictable rate. By studying a white dwarf's temperature and luminosity, we can estimate how long it's been cooling, and hence, the age of our galaxy. It's like reading the rings of a tree, but on a cosmic scale. But the importance of white dwarfs doesn't stop at being cosmic chronometers. They also play a crucial role in the life cycle of the universe. Under certain circumstances, a white dwarf can accumulate enough matter to reach a critical mass and explode in a Type Ia supernova. These cataclysmic events are not only spectacular to observe, they're also fundamental to the cosmic recycling program. Supernovae spread elements like carbon, oxygen, and iron across the cosmos. This stardust goes on to form new stars, planets, and even life. We, and everything we see around us, are made of star stuff, as the late, great Carl Sagan once said. In a way, studying white dwarfs is like studying our own cosmic roots. They help us understand where we come from, how our universe has evolved, and where it might be heading. So studying white dwarfs not only helps us understand our past, but also gives us a glimpse into our future. And that, my friends, is why these tiny fading stars shine so brightly in the eyes of astronomers. Despite what we've learned so far, white dwarfs still hold many mysteries. These celestial bodies, as small as Earth yet as massive as the Sun, are veritable cosmic puzzles. It's as if they're playing a game of hide and seek, teasing us with their tantalizing secrets. For instance, have you ever wondered why some white dwarfs appear to tip the scales, breaching the Chandrasekhar limit? This cosmic rule states that a white dwarf's mass cannot exceed 1.4 times that of our Sun. Yet some white dwarfs seem to scoff at this limit, packing on the pounds without collapsing into a neutron star or black hole. How do they achieve this cosmic weightlifting feat? Well, it's one of the many mysteries these heavenly bodies dangle before us. Then there's the puzzle of their temperature. White dwarfs are known to be incredibly hot, with surface temperatures reaching up to 100,000 degrees Celsius. But over billions of years, they're expected to cool down, eventually becoming black dwarfs. Yet we've never observed a black dwarf. Is it because the universe isn't old enough? Or is there another piece of the puzzle we're missing? And let's not forget the mystery of white dwarf pulsations. Some white dwarfs rhythmically change their brightness, a phenomenon known as pulsating. But why only some and not all? Why this cosmic drumbeat in the silence of space? The answers remain elusive. Lastly, what about their role in the broader cosmic ballet? We know white dwarfs can be part of binary systems, and their interactions with companion stars can lead to spectacular novae and supernovae. But how do these relationships evolve? And what effects do they have on their cosmic neighborhoods? These questions are just a taste of the enigma that is the white dwarf, a testament to the endless wonders of our universe. Each query a starlight spark in the vast cosmic dark, a beacon guiding our quest for understanding. So the next time you gaze up at the night sky, remember, each twinkling light could be a white dwarf, a mysterious and fascinating part of our universe.